Welcome back to OK Calculus. My goal is to explain various subjects of calculus step by step. Last time I talked about limits and how to find them. This time I will cover two subjects that connect, asymptotes and continuity. An asymptote is a line that f of x approaches but never touches. There are two types of asymptotes, horizontal and vertical. Vertical asymptotes occur at the x value where the denominator equals 0. In the previous video I mentioned that we can't divide by 0, but we can get really close to x equals 0. An example of a vertical asymptote would be the graph of f of x equals 1 over x. As you can see, plugging in a 0 gives you 1 over 0, which you can't do. So at x equals 0, you'll notice the line of x equals 0 is a vertical asymptote. Let's look at another problem. This is the graph of f of x equals x minus 1 over x plus 1. How would we find the vertical asymptote on this one? So first, you've got to find out what makes the denominator equal 0. Since the denominator is x plus 1, you set that equal to 0 to find out. As you can see, negative 1 makes the bottom equal 0. Therefore, there is a vertical asymptote at x equals negative 1. There is one more problem that has a twist, which I will show you. F of x equals the quantity x squared minus 1 divided by x plus 1 is the function. You may jump to the conclusion that x equals negative 1 is the vertical asymptote because you set the denominator equal to 0 and found that x equaled negative 1. But look at the numerator. You can notice that it factors out to x plus 1 times x minus 1. Now we can cancel the x plus 1's on the top and bottom. When this happens, as you may know, there is a hole at that point. In summary, when nothing cancels, it is a vertical asymptote, and when something does cancel, there's a hole there instead. In the last lesson about limits, I mentioned that a limit will still exist at a hole, but may not exist at a vertical asymptote. The only time a limit exists at a vertical asymptote is when both sides of the vertical asymptote are going to the same infinity. The second type of asymptote is the horizontal asymptote. This one is much easier to find. A horizontal asymptote is, as the name implies, a horizontal line that f of x approaches forever without touching. We will be finding where f of x is going when you plug in huge positive and huge negative numbers. What you do is you look at the highest power in the denominator and the numerator. These exponents will determine where your graph is going to go. Just think about x squared plus 1. That plus 1 isn't going to do much when you plug in a huge number like 100,000. So let's say that the equation is f of x equals 2x plus 1 over 3x plus 2. Look for the highest power. You can see that the 2x is the highest power on the top and the 3x is the highest power on the bottom. That leaves you with 2x over 3x. Those x's will cancel and you will get 2/3. That means that as this graph approaches infinity, it will approach the line y equals 2/3. Now what is the horizontal asymptote of f of x equals x plus 1 over x squared plus 2? The first step is isolating the highest power, which gives you x over x squared, and the x's will cancel to 1 over x. However, the x's didn't completely cancel all the way out this time, so now you must determine what happens when you plug in large numbers for x. Plug in, let's say, 1,000,000 for x. That gives you 1 over 1,000,000, which is very close to 0. You can conclude that the horizontal asymptote is at the line of y equals 0 because f of x is approaching 0. Now that we know how asymptotes are formed and how to find them, we can move on to continuity. Continuity is similar to limits. They both have rules for determining if they exist at certain points. For limits, the limit from the right had to equal the limit from the left of the point. That meant that even if the point of the two sides we're approaching didn't exist, the limit still existed there. This is not the case for continuity. There are three main rules for a line to be qualified as continuous at a point. So rule number 1, f of c must exist. In other words, if plugged in a 2 into the function, I better get a real numerical answer. Rule number 2, the limit as x approaches that number from both sides must exist. Basically, when you come from the left, you should be approaching the same y value as you come in from the right. And the final rule, rule number 3, f of c must equal the limit as x approaches c of f of x. This means that the point at which you are approaching must exist and still be there. A simple way to sum up these three rules would be to say if you can draw this graph without lifting your pencil, it is continuous everywhere. Let's test these graphs to see if they're continuous at certain points. The first graph is clearly not continuous because it jumps at x equals 1. The mathematical way of saying this is that the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. The second graph is also not continuous at x equals 1 because f of 1 does not equal the limit of f of x as x approaches 1 from both sides. The last graph is also not continuous because f of 1 does not even exist. If you see any of these three instances, the function is not continuous. To sum up these two topics, asymptotes can be described as places where a graph approaches a line either horizontally or vertically forever. Continuity can be summed up as if you were to draw a graph without lifting your pencil, it is continuous. Next time I'll explain one of the most important skills in calculus, derivatives. Thanks for watching.